introduction and also for the invitation. It's really nice to meet so many friends. Also my supervisor Dima here. So today I will talk about the fractional translators in moire graphene. So before I get started, I would like to acknowledge my collaborators. They are my students at Peking University, including Jian Xie, Zihao Huo, 文学网的在哲长. We also got the high quality bond-nitride crystals from the news team. Without these materials, it's impossible to start this kind of experiments. We also got very strong theoretical support from multiple groups. They are Andrew's group from Princeton, my colleagues, Zhi Dasong and Xicheng Xie in Peking University. We also get a collaboration with Jianpeng Liu from Shanghai Tech University. So I think previous speakers has a lot of introductions for the fractional translators. Let me remind you a bit. So actually, it has been theoretically proposed more than 10 years ago. And the fractional translators, basically, it is a lattice analog of the fractional quantum Hall insulators without lambda levels of magnetic field. So in particular, Andrew and Nicola has raised this concept FCI, and in this system, it needs a flat chain band, and also similar, importantly, it needs ideal quantum geometry. So experimentally, the progress has been done. From different groups like Xiaobo Lu's group from Washington, and Shanjie and Qingfei's group from Cornell, as well as Qingxin Li's group from Shanghai Jiao University. So after, in a different system, so by the way, the first system showing the fractional translators is twist MOT2. So after Longju's group from MIT, they observe very similar phenomena in a Rome-Hedro graphene system. They use the pentalayer graphene. So with all these systems, they have some similarities. Like first, it needs a flat chain band, and this chain number is c equals to 1, and it is like dispersionless and has ideal quantum geometry. At fractional moire fillings like 2/3 and 3/5, it opens a gap, and at these fillings, the whole resistivity just gets quantized. So from our side, we start from the Rome-Hedro graphene, like Longju's group from MIT. So actually, for Rome-Hedro graphene, it has intrinsic flat band at low energy excitations. However, this flat band connected to the higher energy band, which is dispersion. And if we further include the moire effect, it will fold the band. In some cases, we just get the isolated flat band. This flat band can be further tuned by the electric field, and in some cases, we get the chain band. So with this technique, actually, people have already observed very interesting results in past several years. For example, Feng Wang's group from Berkeley, they firstly reported the trilayer graphene system aligned to bond nitride. They get a translator with c equals to 2. And also we mentioned Longju's group. They firstly reported the pentalayer, as well as Andrea Yang's group. They reported the tetralayer graphene. All these systems showing chain band, and this two system also shows the fractional translators. So in our case, we choose a different system, slightly thicker. It's 6-layer. So basically, the structure of the device is like this. We have a hexalayer graphene encapsulated by the both top bond nitride and bottom bond nitride, and also dual gate with graphite. So this device has a very small twist angle, close to 0. So basically, we can get the interacted band structure at the moire filling, mu equals to 1. Indeed, we get a very similar flat chain band here. So, but this calculation has been done by Jianpeng Liu's group from Shanghai Tech University. So then we cool down this device. We observe this kind of very rich phase diagram. So basically, this is the longitudinal resistance as a function of filling factor and the electric field. So it's in Z direction. So if we look at this phase diagram, basically we get the correlated state like mechanical barrier graphene at mu equals to 1 or 2, which means we fill 1 electron or 1 hole, or 2 electrons or 2 holes per moire unit cell. If we further look at this region, we zoom in this part, we get vanishing the longitudinal resistance and finite hole resistivity. So if we show it more quantitatively, we can line cut here. We get indeed the vanishing longitudinal value and also quantized hole resistivity just to the noise level. We also get this kind of very standard quantum anomalous Hall effect showing the chain number equals to 1 here. This is very similar to the pentalayer graphene case. And then, yeah. Please. In this one, this part? This part. Yep. So so maybe we can look at this part. Actually, from this part, the resistance is kind of high, and partially, if we even go close to the China neutral point, the contact will be bad. But at 0.7, actually, there are some physics of the fractional translators, which I will indicate later. Yeah, it's related to the fractional fillings. So, yeah, here is it. Then, if we measure the system at magnetic field, basically we measure the same resistivity as a function of carrier density of moire fillings at different outer plane magnetic field. So we get this state, which is starting from the 2/3 moire fillings, and also the slope equals to the 2/3. It's a fractional translators. As well, also we can see kind of signatures from the hole resistivity. Very interestingly, if we further increase the magnetic field, we get the state with opposite slope. So for simplicity, we call it like anti-FCI state. So if the slope changes sign, which means the chirality of the state also change, we also notice that not only the FCI state, all this hole resistivity from like 0.4 to 1 also change its sign, which means the chirality of this system change. And yeah, the right side is mu equals to 1. Yeah, I haven't shown there. Yeah, I will show that later. Yeah. So then we also check this state, which means we fix the carrier density of the moire fillings at 2/3. We change we tune the electric field and the outer plane magnetic field. We get this kind of phase transition, and it can only start from a critical electric field, like 0.2 watt per nanometer. So basically, with this phase transition, the sign of hole resistivity change, and the fractional translator state can survive in both phases. So also this phenomena is absent in the tetralayer and the pentalayer system. And then we further measure this, we have done this measurement in the presence of the in-plane magnetic field. So basically we apply the magnetic field both out plane and in plane. So the first measurement we have done in a very weak in-plane magnetic field, which is very similar to all is neglectable. Like we have FCI state and LTFS state at high outer plane magnetic field. And then we further increase the in-plane magnetic field to 2 Tesla. So apparently the phase diagram changed a lot, which means the anti-FCI state get enhanced, and the original FCI state is squeezed to a very narrow range in terms of the out-plane magnetic field. So as we can see from the phase diagram, if we make a line cut along the trajectory of the FCI state, we can get the anti-FCS state can be quantized to very low outer plane magnetic field, and the original FCS state is suppressed. So if we furthermore more quantitatively, we can see this, we can observe this kind of in-plane magnetic field dependence of the quantum anomalous Hall effect, or it's actually it's a fractional quantum anomalous Hall effect. At 0 in-plane magnetic field, we get this standard fractional quantum Hall effect. And if we apply very weak in-plane magnetic field, so almost nothing changed in the Hall resistance, but we can see the transition for the longitudinal resistance becomes more smooth. It shows a too pronounced peak. If we further increase the in-plane magnetic field, we can see the the fractional quantum anomalous Hall effect just gets completely suppressed. We cannot get the quantized value. So, yeah. Sure. Equals to 1, yeah. Yeah. Yes. Yeah, I will show you in next few slides. I think if I haven't covered that, I will please ask me again. Yeah. So now we can apply both magnetic field, the magnetic field in both directions. So basically, this is the fractional state, or the mu equals to 2/3, and this part is mu equals to 1. I think this is related to your question. So basically, for both states, it can be quantized at both zero magnetic field and finite magnetic field. But this quantization, or the sign of the Hall resistance, can be simultaneously tuned by both magnetic field, and both state follows this kind of elliptical phase boundary. As you can see, the red color indicates the positive chain number, and the blue one corresponds to the negative chain number. So how to understand this? Basically, in graphene system, it's not easy to understand the in-plane magnetic field can effectively tune the Hall resistivity. So generally, if an in-plane magnetic field couples to the Hall resistivity, it can have different mechanisms, but in a nutshell, it can follow either it's an in-plane optical effect. If the system have a non-neglectable thickness, like here is like 6 layers, is not it have like a thickness like 2 nanometers. The other thing is the spin optical coupling. So there are two kind of mechanisms, but if we consider the in-plane magnetic field, the in-plane optical effects of the Rashba spin optical coupling, actually both mechanisms can have some expected behavior. So that means the direction of the in-plane magnetic field will couple to the sign of the Hall resistivity. For example, if we have an in-plane magnetic field pointing to the x direction, we can expect the Hall resistivity is positive. But if we reverse the direction of the magnetic field, we should expect the different or the opposite sign of Hall resistivity. However, in our experiments, if we look at the in-plane field dependence, for example, the positive 2 Tesla and the negative 2 Tesla, which means the in-plane magnetic field just reverses the sign, but the Hall resistivity is constant. It's always positive. It only depends on the direction of the vertical magnetic field or the outer plane magnetic field. So apparently, either so the previous two mechanism cannot explain our observation. So we have the third mechanism which could be possible to explain this phenomena. So basically, our colleagues Zhi Dasong and his student Xi Chen proposed the possible mechanism. Basically, consider the intrinsic of the icing spin optical coupling. So with this model, the Hamiltonian can be simply in this form. It contains 3 dominant terms. First is the optical magnetization, and the second term is the spin term, and the third one is the spin optical coupling. This is the 3 dominant term. So basically, if we look at this formula, and So the first one, the third one is negative, and the second one is positive. So if we set some limitations, like if the MZ or the optimization is smaller than mu b, that means if we increase the outer magnetic field, in some case, the energy will be lower when the value or the tau z change from k to k prime. So this basically can explain this phase transition at a finite outer magnetic field. However, if we further increase or if we further apply the in-plane magnetic field, basically we just get one more term in this part. And if we solve this equation, we get these two eigenvalues. We follow these results. So if we consider the phase boundary, it needs these two eigenvalues equal to each other, and we get this relation, which is indeed elliptical manner. So by fitting the experiments with the theoretical model, we get the two important parameters. The first one is the strength of the spin-opposite coupling, which is like 40 micron electron volts. It's kind of similar to previously theoretically proposed, but here we firstly show such a low value of spin-opposite coupling can really dominate the behavior of transport. And the second result is we get the magnetization, or the orbital magnetization is like 0.4 mu b. So far it looks all good. However, if you look at the experiments at 2/3, actually, so for these dots is from the experiment, and this curve, or this red curve, is from the theory. At low magnetic field, it looks okay, but clearly it has some deviation at higher in-plane magnetic field. So this is the first problem. So the second problem is the discrepancy with the Hartree-Fock calculation. So as I just mentioned, the previous model has some very strong limitations. For example, we need a value chain number, which should be negative, but from Hartree-Fock calculation. So actually the value chain number is positive. The other things, from this model, the orbital magnetization we get, or the value, is much lower, or more than 10 times lower than the theoretically proposed, like 5 mu b. So with this theory, looks like the theory of the spin-opposite coupling can quantitatively explain the overall trend of the experiment, but it has some very strong limitations which cannot be clearly explained by the current theory, like from Hartree-Fock calculation. So far we don't have some clear understanding about this, and for this part, Andrew and his student Eve have contributed a lot. So this is the first part of my talk. Basically, it's related to the fractional translators in the hexagonal bond-nitride aligned to moire graphene. It's a 6 layer. And so for the second part, we try to understand what really affects the topology in this system. The first one is the stacking order. For example, we know for bond-nitride, actually this is if we consider the top layer, actually is break the inversion symmetry. And for moire graphene, it also breaks the inversion symmetry. So if we align the two layers, actually, even we get a same twist angle or same moire wavelengths, actually we have two different stacking geometry. The first one we can, it's shown in this slides. So experimentally, it's very difficult to quantify because we just measure the moire period. So, but we cannot really get which is like epsilon equals to 1 or which is equals to 0. So the second thing is how the twist angle affect the band topology, or how it affect the translator or fractional translators. So to address these issues, first we figure out a technique to really get the two configurations. So we take advantage of the atomic step of the bond-nitride. For example, you have a substrate, there is an atomic step in the left side, there is one more layer. So in this stack, basically we get one stacking geometry, but in the right side, we get the other opposite geometry. And at the same time, this sample can have very similar twist angle or the Moire wavelengths. So with this technique, basically we get the two devices, or with one stack, we get two devices. One is, but both are close to 0. So actually, to get this architecture, my student Zihao Huo and Wan Xuanwang really make a lot of effort to identify to get this structure. So first, they carefully check the array bonitride to find this atomic step. Basically, it should have like 0.3 or 0.4 nanometer from the FM image. The other things, we double check this flake with the optical technique. We use a laser, we shine on the sample, and then we measure the second harmonic generation. So basically, if the HBN has odd layers, so in general, it breaks the inverse symmetry, it can give very strong the second harmonic generation. But if there is even layers, basically it keep the inverse symmetry. We should not expect the second harmonic signal. So basically, this is the from the same stack. Indeed, if we measure the left side, we just get nothing. But if we measure the right side, we get a very sharp peak, which corresponds to the odd layers. So with this all carefully calibrated, we get the device and cool down the device in the cryostat. We first focus on the integer translator state at mu equals to 1. Indeed, for both stacking geometries, it can stabilize the topological flat band, which means we observe the quantum anomalous Hall effect with the chain number c equals to 1. So, so far, this state, we have shown that both stacking geometries can stabilize this state, but in the more distant side. So actually, the FCI state also observed in this slide. And then we further measure all the devices at different twist angles. So basically, I show the twist angles from very small, like close to 0, to twist angle close to 1 degree. So as we can see, the left figures shows the longitudinal resistance, and the right one shows the Hall resistivity. So basically, the dark blue and dark red correspond to vanishing longitudinal resistance and quantized Hall resistance. So with the twist angle increasing, we get the translator state moving to higher electric field. And also the range in terms of the electric field becomes narrower. And finally, if we look at this device, it is still has translator. But it is, although it becomes smaller, but it still has a translator. However, if we further move to 1.1 degree, so which means the twist angle get to a critical angles, so the c equals to 1 gap clearly closes. So if we make a line cut at mu equals to 1, we get all this this data set from almost 0 degree to 1.1 degree. So from 0 degree, we get vanishing longitudinal resistance and quantized Hall resistivity. When it's moved to the 1.1 degree, we just get a trivial state without quantization, without a minimum of the rho xx. So we summarize all these device or the data points in a phase diagram. So clearly we show with the twist angle increase, the c equals to 1 gap close and finally close at 1.1 degree. So this is very clear from experiments, but theoretically, this is not easy to understand. So this is I will show you LFCI in the next slide. Okay. so this is for the integer state. It's very clear from experiment, but if you check the Hartree-Fock calculation, basically this is done by Andrew's group, also collaborate with Nicola. So I think this kind of calculation has been done widely in this community, but the trend is actually opposite with experiments. So basically the energy difference between the C equals to 1, the topological trivial and non-trivial state gives the ground state. For example, from the high trivial calculation, actually it gives the C equal to 1 or topologically non-trivial state at large twist angle. At small angles, it gives opposite results. Apparently, it is opposite with our experiments. So, very remarkably, I think Andrea and his team has figured out how to what happens in this process. So basically, they carry out the exact diagonalization and also as well as the generalized random phase approximation method. They can really reverse the trend and reach is kind of match the experiments. I think I will not go to detail since Andrew is here. I think he can answer some possible questions here. So this is our second work, basically for the Rom-Hedro graphene system. Here, for example, is in hexagonal graphene. We show two things. One is the stacking geometry is not that important for the integer state, and when the twist angle increase, it can have a clear trend for stabilizing the translator state. So far it's still for integer state. What about the fractional state? So first, let's look at the device at a small angle. It's not, but it's not that small, but it's like 0.5 degree. And it has clear C equals to 1 state. And at C equal to 2/3, we can have this strata formula like dependent fractional translator state, also showing the phase transition. It's not quantized, but it shows this signature. Not that good like the smallest angle. And then we increase the twist angle to like 0.9 degree. So we still have a gap opening at 2/3. But in this case, we get a translator, not fractional translator. The chain number equals to 1. So if we further increase the twist angle to 1.1 degree, or the largest twist angle, we get nothing at 2/3. It's the topologically trivial metal state here. So basically, this is the evolution of the fractional translators in terms of the twist angle. So which means for the FCI, it also needs small twist angles, and the critical angle is also is smaller than the integer state. Yeah.
Starts out being -1, but at some critical magnetic field, the -1 survives, and you also get a +1.
Yes, at finite magnetic field, we get both -1 and +1. For the fractional, it can only compete. They compete. You can either get positive or negative. But yeah. So this is the second part. Basically, we show the twist angle dependence of the topology. So it contains integer and fractional states. So what's the next? Actually, theoretically, if we consider the flat chain band and the traditional lambda levels, there is some difference. One of the most difference is it is possible to have a chain band with higher chain numbers. If we further fractionalize this system, it could give some new state. Right? There are a lot of theoretical papers discussing this kind of phenomena. So we try to actually we have some effort for doing this, and we try to have some new systems. So basically, we consider a new system made of the twist Rom-Hedro graphenes. From the very beginning, we use it's like a trilayer graphene twist on another trilayer graphene. So both are with the Rom-Hedro stacking. So with this system, basically we have like the moire band folding because there's moire modulation. There's interlayer interaction, just like magic angle bilayer graphene. But for the Rom-Hedro graphene aligned on HBN, there's no interlayer interaction. And here we also have the intrinsic flat band because as we mentioned in previous slides, So at low energy excitation, there's a flat band. So by have these three effects together, we should expect there is some new topological flat band. So at the first, we need to figure out how to have this kind of device. As we know, the Riemann stacking is metastable phase. It's always like to relax to the Bernal stacking. So if we have one layer, it looks fine. If we have one layer twist on the other layer, we have more possibility to have either one layer or both layers relax to the Bernal stacking. So my student really developed this kind of high throughput fabrication technique. Basically, once we find the Riemann graphene, we will cut this graphene into many pieces, like 2 sets. Like each set include like 5 or to 10 pieces. First, we pick up one set, and then we twist on the other, like 5 samples. But with this process, we will get like 5 to 6 devices in the whole stack. So since we have a lot of samples in one process, even we get like relaxed in 1 or 2 samples is still fine. At least we can still use some of them. So this is an example. We have 6 twist regions, and I think there are maybe 3 half relaxed to Bernal stacking, but still 3 left. So with this device, we show the twisting angle. I think it's like 1.2 degree, more or less, and they will have measure it. So basically, this device shows very clear translators with the C equals to 3 at mu equals to 1. So basically, first we get the high chain number flat band, and we show very standard the fractional. It's not fractional; it's the integer quantum anomalous Hall effect, and with the Landau diagram persists to the exact 0 field. So this is at 1.2 degree. So all integer without fractional. Then we change the twist angle to slightly larger values. So this device shows a twist device at 1.6 degree. So there is some difference. So first, if you look at the mu equals 1 state, in the small angle device, it shows a C equals to 3 translator. But here it's a trivial state without any anomalous Hall effect. But we got a translator or the quantum anomalous Hall effect at fractional fillings. They are at like half or the 1/3, 2/3. Sorry, it's a quarter and 1/3 and half. So we zoom in this part. Basically, it shows the longitudinal resistance and the Hall resistance as a function of the D field and also filling factors. If we make a line cut in this direction, we get minimums of the longitudinal resistance at quarter, 1/3, and half. At the same time, we get quantized value, all quantized to or C equals to 1. So in this case, we get integer translators at fractional fillings, but not FCI. So actually, there are some understanding why the behavior of the 2 devices is different. So first, if we look at the 1.2 degree, so we have the C equal to 3 gap at mu equals to 1. Basically, there is a flat band. We fill 1 electron per unit cell. We get partially filled for the fold degenerated with flat band. And in this case, we get a very large interaction compared to the kinetic energy. Then we get this kind of single flavor polarized chain gap. So if we look at the large twist angle device, if we set the moire filling to mu equals to 1, actually the chemical potential should locate at the dispersive region. So in this part, actually the kinetic energy is almost similar to the interaction energy. So we just get a metallic state. But if we set at fractional fillings like quarter or 1/3, it still move downwards, and we get this kind of interaction gap. And in this interaction gap, we get the topologically non-trivial state. So basically, my colleagues Zhi Song and Yijie Wang have carefully calculated these systems. Indeed, for the small twist angle, it's showing a very flat, in particular at mu equals to 1. So basically, this is the non-interacting band structure. And for the large twist angles, so indeed, it has some dispersive region at larger moire fillings. So it's kind of consistent with our expectation here. So recently, actually, there are some other development from other groups. So basically, this is a work recently posted by Guangyu Zhang and Wei Yang's group from IOP, China. So they use a very similar but slightly different system. Yeah, sure. Okay, I'm almost done. Yeah. So this is almost similar, but they choose barrier graphene stacked on the tri-layer graphene. The tri-layer graphene is Romhezhou. So for their device, they observe also the C equals to 3 chancellor state at some integer fillings. For example, at mu equals to 1, they observe the C equals to 3. At mu equals to 2 is a trivial insulator. And at mu equals to 3, they observe the C equals to -3. So basically, this is the integer state. However, very interestingly, they can figure out some signature of the FCI state at fractional moire fillings. For example, from their paper, they show a translator at like 12 to the fifth with the channel number like C2 and at the second FCI state in the second moire band. Sorry, I think it's the third moire band, but it shows some even denominator stuff. So basically, with this slightly different twist, there are some apparently different physics in this direction. So I think I will stop here and give the quick summarize. So first, we have demonstrate the both integer and fractional states at the 6-layer graphene aligned to a bond nitride. So both integer and fractional state has critical angle dependence. For example, for the integer state, it needs a twist angle smaller than 1.1 degree. For the fractional state, for example, at mu equals to 3 and C equal to 3, it needs a twist angle smaller than 0.5 degree. So the third part is both the FCI state and the integer state are very sensitive to the implant magnetic field. And possibly because of a non-lignitable symmetrical coupling here. So we show a new platform for the topological correlated physics by twisting the Romhezhou graphene system. I think I will stop here. I'm ready to take questions. Thanks a lot. Yeah.
Concerning the spin-orbit coupling, Eli Seldorf from the Weizmann reported experiments in a very similar system, according to which the spin-orbit coupling was like 140 microelectron volts.
Yeah, that's true. So first, their system is tetralayer graphene without moire. So indeed, the magnitude is like 3 times larger in our system. So we are not sure whether.
Why do you think it's larger?
So apparently their value is 100.
Okay.
Yeah, their value is larger, but we don't know whether the thickness of the system or the moire can affect this coupling strength. We don't know.
Thank you. Andre? Okay.
So, we're all friends here, and I wasn't the referee of any of your papers, but how can you show me where's the even denominator state? Like, and how sure are you that it actually exists?
So you mean this work, right?
Right.
Yep. Actually, I would see this, I can only see there's some signature, right?
Yeah,
so first of all,
what do you mean by signature?
First of all, this state is not quantized. Okay. So the Hall resistivity is not quantized, and the longitudinal resistance is not vanishing. So they only observe this kind of magnetic field dependence, but this slope really corresponds to the fractional quantized value, and it can start from fractional moire fillings. So this is I think this is the only evidence from their paper. Yeah.
How low does OXX get in the FCI states?
Yeah, this is a very good question. So actually in our system, the rho xx is still very high. It's like half value of the rho xy. It's like 10 kilo ohm more or less.
I see.
So I think
So if you are 2/3, OXY is 3/2, and OXX is like 20 kilo ohms.
I think let me show you. I think I have the exact value here. I forgot. I think it's more like 10 kilo more or less. It's like here, right? So here should be like 10 to 15 kilo.
25.
Yeah.
So it's close to 20 kilo.
Yeah. Yeah, still very high.
Do you have any feeling why? I mean, this of course.
I think it's more depends on the sample quality because so if we look at our device, actually there's so the two leads we measured, the rho xx is like a few micrometers, but the rho xy is like 1 micrometers. So if there is some inhomogeneity, for example, only one part showing the FCI, probably we get this kind of very large resistance. So of course this is one possibility, and the second thing is maybe just because of temperature is not low enough.
What's the temperature?
We don't know the exact electronic temperature. So our system showing millikelvin, but we don't know the exact. It depends on the filtering stuff. Yeah.
Thanks.
Any more questions?
Sort of perhaps naive question.
Sure.
Your system, presumably, since there are a lot of bands, there's some band structure effects and so on. But it seems to me that when you're interpreting some of the data, correct me if I'm wrong, and try to extract how the filling factor relates to the churn number, somehow you're using, sort of neglecting a little bit the crystal structure or the bands, right? Because in some sense, if you in a very naive way, you have the Moire-Claro relation, which relates the filling factor for, let's say, the integer case, with a term that involves, I don't know how to call that, the S topological number, which involves the screening that the lattice does to the charge, and another piece, which is the churn number, which is associated with the quantum Hall effect. And you don't seem to be seeing this here. So the lattice is doing nothing?
Yeah.
Or the Moire-Claro relation doesn't apply?
So I'm not sure whether I understand the question. At least from the experiment, we see all the translator states, all the fractional.
But you know the Moire-Claro relation, right?
He's asking about the intercept. It's killing intercept.
Yeah. I mean, so if I try to understand, but maybe
I might say something
you can comment.
You, the expert.
Sorry.
You didn't pay attention. Okay, sounds good. What I was trying to say, that it seems to me that from the experiments, he's relating the filling factor in a lattice structure of the system directly to the churn number. And I remember in my undergraduate days, right, there's a relationship called the Moire-Claro.
He's using that. He's reading off the slope in the magnetic field.
Right, but are you using that
Yeah.
or not?
Yeah.
Because it seems he's taking the S, the topology, the other quantum number.
Yeah, we
into account,
calibrate the other current density with the lambda Venn diagram. It's in case if we find the linear, so all this churn gap or the quantum Hall gap follows a linear behavior in the phase space in terms of the gate voltage and magnetic field. So in that case, I'm not sure whether this is your concern or not.
So he gets sigma xy from the spreader formula. This is this linear line.
Yeah.
But I think what you're saying is that sigma xy is not necessarily the ratio of the.
Well, I'm saying that nu is not directly proportional to the churn number. The filling factor in a lattice, there is another term which includes the screening of the lattice, right? And that's also another integer, but it's a different integer, not the Chern. So I'm a bit confused because it seems to me that you extracting the relationship between nu and the Chern number by a direct proportionality. There's no constant additional term in front.
I think it's easier if you just show your color plots.
Yeah.
I think it's very easy answer.
So probably from this one, right?
Yeah.
So I think your question is, so this is the chain number is equals to 2/3, and your comment is not necessarily to start from 2/3 Moire filling, right? Or is that your concern?
Yeah, the nu has to be that piece plus some other one to get the right value of nu.
Yeah, but I mean, so first this flat band has chain number equals to 1, right? So if you have the whole field gap at mu equals to 1, you get integer translators. So this is clear. And so at fractional fillings, so if you consider all this quantum geometry is uniform.
I was even, okay.
So of course we can expect this kind of.
Yeah, we can talk later.
Okay. Yeah. Thanks.
Let me see if there is any fast question or fast last question. If not, then let's thank the speaker one more time.
Yeah. Thanks.
And